identifying whether sugars are D or L sugars, ketoses or aldoses, and how many carbons they have is really mechanical and straightforward. You could have something like this. It has 1, 2, 3 carbons. That makes it a triose. That's our N-ose. Has an aldehyde on the end. It's aldo. So it's an aldo triose. And go down to the farthest chiral hydroxyl group from the aldehyde. It's on the right in this Fischer projection. So it is a D sugar. Let's go with something longer. Put the OH over there. We find the ketone. Go to the farthest chiral carbon and see that the OH group's on the left. This is an L sugar. It's a ketone. So it's a keto sugar, and it has 1, 2, 3, 4, 5, 6 carbons. So it would be a hexose. And it is that straightforward. You need to know your prefixes: tri, tetra for tetros, penta, hexa. Those 4 you may have to use, but that's all there is to it. I'm going to now go into a broader application. Let's try to identify these things in some more complicated pictures of sugars. This infographic is available on Compound Chem and on your learning management system if you're in one of my classes. And I'm going to zoom in on it. I'm going to have to adjust it another way. The digital zoom isn't functioning. So here we have some different representations of sugars that are not in their Fischer projections. So let's take a look at them and highlight the parts that are going to help us understand. Well, first off, we've got a clue that these are all naturally occurring. So they're all going to be D sugars. But let's identify the place where we would need to look to determine that. So our first thing is going to be, is it an aldose or a ketose? We're going to look for a carbon with 2 oxygen attached. And as you look around this molecule, this is the carbon with 2 oxygen attached. And I'm going to do it. It is in fructose. In glucose, it's there. In sucrose, we've got 2 of these. There's one, and there's the second. Let's try to determine if those are on the end of the molecule or in the middle. So this one here has a carbon going each direction. I'm just going to put a little K there. That's going to be a ketone. This here has carbon going one way and hydrogen going the other. That's an aldo sugar. Now here, this carbon has carbon going down, carbon going up. That's also a keto sugar. This is fructose, just like here. And here we have carbon going one way, hydrogen going the other. Well, this works. This is the glucose molecule, like this one here. You put fructose and glucose together and you get sucrose. Lots of interesting stuff you can read from this graphic. Sucrose is defined as having a sweetness factor of 1. That's our standard. This is table sugar. And other things can be more or less sweet. Like fructose is sweeter. So when you get high fructose corn syrup in things, less sugar tastes sweeter, or the same amount. Less sugar can taste as sweet, or the same amount can taste sweeter. So we've figured out aldo or keto. Now where the D or L would be determined, I do not expect you to be able to do this from this kind of projection, but we would go to the carbonyl, to the carbon atom, the last chiral one farthest away. So that's the point in fructose where we would decide if it's D or L. Here it would be this carbon in glucose, and of course the same points in the glucose and fructose molecules in sucrose. Let's move over and take a look at sugar alcohols. They're another natural sweetener. And you say, how can this be a sugar? I'm going to take one of these and draw it as a sugar. Let's take sorbitol. Actually, I'm going to go with erythritol. So you'll notice there's no keto or aldo group on this, but it has 1, 2, 3, 4 carbons. So if I convert it to a Fisher projection, it's going to have 4 carbons like this. Now, as a naturally occurring sugar, it's going to have the OH on the right. That's going to be an OH coming out towards us, which will actually correspond to this OH here, I believe. H would be towards us in this diagram. So this one here, yeah, the way it's drawn, it's going to be the same either way we go, because we rotate things around to place them. It'll be the same either way, whichever it is. They're both the same. Okay, and we've got an OH on both ends, in the sugar, one of those would be an aldehyde. So by reducing this sugar, adding a hydrogen here and here on each end of this double bond, you turn it into an alcohol and make erythritol. It is a little less sweet than sucrose per molecule, a little less sweet than sucrose, but these sugar alcohols, we don't get as much energy out of them when we digest them, so they're a little bit lower calorie content than the sugars themselves. Let's take a little more time. Take a look down at this molecule from monk fruit. Monk fruit has a molecule that is considerably sweeter than sugar. A factor of 250 to 425 times in relative sweetness. But you can see in here, we've got rings with these functional groups commonly found in sugars, acetals, which we know form from ketones or aldehydes. You've got them in each of these molecules. And then there are all these other OH groups coming off. So these are sugars. There are 5 sugar molecules, 5 sugar monomers in this bigger, very sweet molecule. Here's a ring you might recognize. 6-membered, 3 6-membered rings, and then a 5-membered ring. There's a steroid ring. So sugars connected to steroids make very sweet molecules. This is just one example. They have other biological effects as well. You may learn about. So we've got a lipid connected to carbohydrates. If we look over at steviosides, here are 2 very sweet molecules from the stevia leaf, and they have not exactly the same ring structures. There are 2 6-membered rings, but then there's a 7-membered ring here. So this is not a steroid ring, but it does have 3 sugars and 4 sugars connected to the molecule. So this sugar structure in different forms, even if it's all alcohols or it's connected into bigger molecules, our body seems to often taste as sweet. And we could go through these, you could go through these for practice and identify, is it an aldehyde or a ketone? We can mark these acetal groups. Oh, I marked that one wrong. And in each case, this just has 1 carbon coming off of it. This has 1 carbon. This has 1 carbon. 1 carbon. 1 carbon. So in every case here, these are at the end of a carbon chain. So these are all aldo sugars that we're looking at in these steviosides. And then we want to ask how many carbons are in each. So we count them. 1, 2, 3, 4, 5, 6. That's a hexose. 1, 2, 3, 4, 5, 6. Another hexose. We could go on through all the molecules in that way. To tell if it's D or L, we would need to convert it to a different structure or learn to a Fisher projection or learn the way to recognize those in this more three-dimensional representation. But that's beyond the scope of what we're going to do.